Now, in this chapter, chapter 3b, we are going to look at some examples of assembly language program. So I will go through a few examples, how to write the assembly language program, and then you need to write, I have some exercise for you to try it out. Working with the W register, let's see how we write a small assembly program. This program increments the 8-bit working register, which is the W, by 1 repeatedly. So again and again it's going to increase, you know. So if you have a counter, if you have an 8-bit register, if you will start with 0 and then you go 1 and then so on, and eventually the all will be 1, 1, 1, 1, and then if you add another 1, then it will be reset to zeros, right? So it's continuously doing that counting in this case. So how do we write an assembly program? So we have got a counter, we are going to keep adding 1 to it, to that particular counter. So this is a configure command for microcontroller. This assembler will look after this one. You don't really need to rewrite all of these. And then the data for the microcontroller. So all these you don't need to worry about, where it starts and which location and all sort of things. And it's all looked after by the assembler. What you need to say that the start address, where are you going to start? Start address is hexadecimal 00. So it defines the start address of your program, force program to start at this reset vector. And then you're saying go to start. So it will look for the start position. Start is you've already labeled here, and that's where it sees the first instruction. So the program must start from this address, or hexadecimal 0 mean the program counter is set there. And then it will immediately jump to an address which is the start. We don't need to put the value and hexadecimal. Assembler will know what value, it will assign that where the program is. So it starts, program starts from 005. And the first line in the program says clear W register. So clear W register means 0 is put into the W register. As soon as you do that, the 0 flag of the starters register will be equal to 1 because it's affected. So 0 flag of the starter register is that one. That will be equal to 1 at the time. Then you go to next instruction. Next instruction says add, L stands for literal meaning a number, to the W register. The number is 1. So you're adding 1 to it. So you are now, you had cleared everything, 0, 0, 0, 0, all 4 zeros. Now you're adding 1 to it. Yep. And you add 1 to it, and the content, W content, and add 1 to it, and the results will be in W. And then you will find the starters register, because you did the addition operation, the starters register, 3 bits will be affected. C will be affected, that's the carry bit. This is the carry bit between the 4th and the 5th positions. That's 8-bit data. This is the 4th and the 5th one. You don't need to use them now. And then with the results of 0 or 1, results of the addition. And then you're saying go to command to loop. So that means it jumps back to that address and then keep adding another 1 and then go to loop. So the counter keep counting 1 plus 1 plus 1, and it all goes FFFF, you know, 2 Fs like hexadecimal. Then it go back to 0 and keep continuing that. And as I said to you earlier, you would have seen this one, and you clear this register and you keep adding 1 to it, and this will keep going, and the addition of this one, additions all happen there, this is fed here, and it affects the starters register, these 3 bits. And by looking at the bit, you will know whether the content of the register is 0 or not. So that's a very simple example to demonstrate simple assembly language program. Let's look at the next program. This is an example where we want to do 16-bit addition. Remember, the working register is only 8-bit. The microcontroller is only an 8-bit microcontroller. But how do we do 16-bit addition if you have an 8-bit microcontroller? I mean, this arithmetic logic unit is only working with 8 bits, arithmetic, not 16-bit. So we have to do 16-bit. So this program adds two 16-bit numbers that is represented by 2 bytes. So here it is. You will have, that's 8 lower byte, and that's the higher byte of the first number. The lower byte and the higher byte in the second number, you're going to add them. And when you add them, lower byte sum and the higher byte sum, you need to store them. So you cannot store them in any register in one go, but you can store them consequently, contiguously next to each other if you want it. So what you do in the program is, I didn't write the start, the header of the program. You know what the headers are. You don't need to worry about it. I have to configure the data. I'm going to call this as lower byte 1, and I'm saying equal where the memory location 20. Higher byte 1, that is that one, HB1, and memory location 21. Then this is 22, this is 23, this is 24, this is 25. And then if I have a carry going from here, when I do the addition, I need a carry location to have carry as well. So I have got carries on that location, then the results have to be stored here. So I need 1, 2, 3, 4, 5, 6 with carry, 7 locations to do this particular additional operation now. So I will go to my data memory, not the program memory. I select the bank, I know the bank 0 there, where I will say 20 is my first lower byte, higher byte, lower byte 2, higher byte 2, that's the low byte sum, high byte sum, that's my carry going from here to here. So I've told the assembler, keep me all these locations for these variables. It does it. Next bit. Naturally, you have to organize the assembler starting at H00. That's where the prefixed instructions there. That tells you, the instruction tells you, go to start, so it comes to start. Normally, you want to clear this carry location. You don't want anything here. You want 0, 0. So you cleared it already. You can clear it here, or you clear later as well. If you want to clear here, it's okay. Now, what data we put in here? Lower byte 1, lower byte 2. So we need to work it out where you're going to put data and what data you're going to put. So we say we're going to put, I arbitrarily selected data H4F. I said I want to put 4F into my first memory location, which is LB1. That's where. So I go move literal W with the value of 4F into the W register. I have it in the W register. So I have a W register here. I moved 4F it. And from the W register, I need to put them into the memory here. So next says, move my W register content to my memory location LB1. LB1, I've already defined them as 20, so it automatically put it in here. This one has got value, which you will see, 4F. Here is that, 4F. That's 4, that's F. Then second part, so this is done, 4F is there. Then high byte also I want to put 4F. I don't have other data, so I just said copy the content to HB1. HB1 is H21. H21 is this position, and it's this also have got that position. So those two I put values in it. Next thing is I want to put a value here, because here I select any value in this case. So I select a value HC. I put them in here. That is, move the value W from W register to F there, W register to there. So I move them. So I have done LB2, that one and that one. That is LB2 and HB2, same value, you see. I've loaded. So my memory locations are with these values. They're all available now. My memory location is loaded with all the values. The values, that's there, that's loaded, that's loaded, that's loaded, before I do any addition. And also I have to make sure that when I do the carry, I need to make sure that I have the carry added to it as well. Okay. Okay, we just continue. So we have done the low byte addition. We have added on that. We have added that one. Sorry, we have loaded all the values, not added, sorry. We have loaded all the values. Now we are going to do addition now. Now we have to clear the carry, which we have already done it before, so we don't need that instruction. I just put it in to make sure in case we didn't do it earlier, we have to have it always. So it's always good before the main program to clear this location. Once you clear it, that will be all 0. Now you can see this memory location has got all the values stored, and the next memory location has all the values stored. Now we need to do the addition. We need to add LB1 and LB2 together and get the carry out, and then add that one together and put the sums in the right place. So let's do the addition now. So take my LB1, the contents of LB1 to W register. This 0 tells you move to the W register. So LB1 content will be moved into W register. That's instruction. Now what I do is that I add LB2 content to the W register. So low byte addition, that is, result is stored in the W register. So add W. So whatever W has now, W register will have the content of W register is the value we had 0, 1, 0, 0, 1, 1, 1, 1. That's the content of W register. We are saying now add to the W register the value from LB2. LB2 is 1, 0, 0, 0, 1, 1, 0, 0. So you add them. That's what it says. So we add that one. When we add them, this addition is completed, and we need to store them in the low byte sum. Low byte sum is this location, 24. So we just say move the content of W to the memory location, which is low byte sum, which is LBS. LBS is already defined as 24, and we have the equate directive, so it will automatically store that. Once it has stored the value there, we need now do this addition, next addition. These two should be added, plus the carry coming from here should be added as well. So what we need to do, we don't know whether the carry is 1 or 0. So what we need to do first, after this addition, you check the carry bit of the status register. So you go and say bit SC status. So you're saying if the carry bit is 0, carry bit this was 0, then there's no carry. Then bit is 0, the carry bit 0 is equal to 1. Then we execute the next instruction, because bit 1 means there was a carry. If it's 0, if that position is 0, if this is equal to 0, that means there was no carry from here to here. Then we skip the next instruction. This instruction is not executed. So let's say we execute this instruction first. So there was a carry. When you add them, there was a carry. So what happens is that we execute this instruction. This instruction says BSF, you set least significant bit of bit 0 to 1. So we know that the least significant bit of the carry was defined as, in earlier cases, that location. The least significant bit is that, you set that to 1. So what happened now is, you're going to have that, plus you're going to have 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. That 1 belongs to from this carry. Okay, so once you do that, just give me a second now. Let me rub this out. think about a bit. So this instruction I'm at now. So I've got, now I go and move this high byte value into the W register. That's what I have done here. Move high byte value into the W register. And you add the high byte 2 value to the W register content. So we now add this one. This is in the W register. We add the content of this one in the memory location to this one. That's what you did. Plus, we are going to add the carry. Carry is already set. So that's the next instruction, says that add the carry as well. Carry, this one will be 1 already. So it can add that one as well. Once we have added that, the W value, W will hold the final results of the high sum, and you move them to HBS, which is this location here, 26. So you move this one to 26. So this is if your carry is set. If your carry is not set, what will happen is this instruction will go directly here and just move this one. So this one, when it does the addition of this is all zeros. So the answer will be correct. So just go through this again and see whether you understand this conditional instruction here. The instruction here is conditional. So understand and see whether. So in summary, we loaded 2 data here. We did the addition to it, and we loaded that as well, the sum. That's the 8-bit addition. We then check the carry from the starter bit, and if the carry was 1, we made this position 1. We put it as 1 here. If the carry wasn't 1, we left this as it stands, as 0. Then we loaded this data into W register. We added this data to it, plus we added the carry, where they automatically carry set all zeros and 1 or all zeros, add them, and the results is then stored here. So these 2 bytes will have the addition of the 16-byte data. 16-bit data is in there. There's 8-bit there, 8-bit there. That's how you do the 2 8-bit addition. It's it's good for you to run through this again yourself, rewrite it, and you can execute it. The lab demonstrators will show you how to execute this on the computer. And it's good for you to first write by hand on your notebook and understand. You don't need to follow this procedure. You can do other ways as well. So I think it's very important for you to try out a 16-bit addition and see whether it actually works. Do one addition with the carry coming out of here, do another addition without carry coming out here, and select this data accordingly so that you can work out carry comes or not and see the results. Okay? We have now done the 2 8-bit addition, 16-bit addition, right? Now we look at the input-output ports. How do we program input-output ports? So you know, in a microcontroller, we looked at it. There are port A is written as RA. Then you have got port B, 0 to 7. Then you've got port C and port E as well. So there are 25 general purpose input-output pins available. Some of them are analog input, some of them are digital, some of them you can program them as analog or digital. And we need to know how to do it. So a couple of initialization you need to do before we use the port. So for these are bidirectional port. We've got ports A, B, C, and E. And the input pins are direction. Each pin is individually configurable as an input or output. You don't need to have all of them input, all of them output. Individually you can configure them. And it's controlled by, for port A, it's called trish A, port B, tris B, C, and tris E. These are the 4 ports and 4 registers there. And you need to program that. If you put a 1 in tris register, that corresponds to digital input, the input. So in this case, I take tris A register and I go to bit 7, that's that one, and I put as 1. So I've got bit 7 as 1, That means PA7 in figure below. And if I put a 0, and here I put a 0, and that belongs to PA5, that's an output. And this was an output. So you can see what I've done here is, I want the input, so I want to connect a switch to it. So I need to program this as an input port. So I need to put a 1 in the trish register. Then I want to glow LED, so I need to make this port as connected to LED as output. So I put a 0 there, and this become an output. Now you could write the data. If you put a 1 here, it will glow. If you put a 0, it won't glow. This is actually setting, this register is setting your port A as either input or output. Now you could write the data into port A. And similarly, like you can see, these two are 0, 0, therefore they are output program. These are 1, 1, they are programmed as input. That's 0, programmed as output. This is 1, this programs as input. So that's how the port A, once you have written an instruction to it, and the data will be latched on. These have got latches in it, so they will store the data. Let's look at the next one. Now you take port A. Now, when you are going to use port A, there are 3 operations you have to do. There are 3 operations you have to do. You have to know, you need to decide, is port A I'm going to use as a digital port, input port? Is it going to be digital port, output port? Or it's going to be analog port? That's you are going to decide. So in order to decide, you need to put appropriate bits in 2 registers. Because I'm going to deal with port A, as A mean, I got trish A, then I need to get ANSL register. These are all in register banks, and you need to access them. So I go and look for ANSL register. I know port A is in bank 0, so port A is in, this is bank 0, this is bank 0, this is bank 1, and so on. So if I look at port A is here, 0.05 location, that's port A. And then trish A is in another bank at 85 location, and that's trish A. And also I need to have ANSL, because I don't know whether it's an input or analog or non-digital. So I need to look at ANSL. ANSL is in that location. These are the banks 0, 1, 2, 3 registers, and you need to look at the appropriate location. The assembler will know all these commands. If you say to assembler status, it knows where the address is. If you say to assembler port A, it knows where the address is. You don't need to give the address. You can give, or you can say port A. So if you look at this particular example, what I've done is that if I put ANSL, all of them as 1, then they are only analog inputs. And that means analog input means trish A also should be 1, so that I can read the data. If you make ANSL all zeros, then it becomes digital. Then I don't need to worry about it. I go to trish A and say I want 4 of them digital input, 4 of them digital output. So digital input means you're going to put 1 in trish A and zeros in out, and it become as, you know, digital 4 input, digital output. So remember, when you want to program a port, when you want to write a data, or when you want to receive data, you need to do 3 operations. One is to set up the ANSL register, and then set up the trish A register, and then you write or read the data from port A. So you can read through this one. All I've explained is all explained here. Now we are interested in port B. Port B. So again the same principle. In port bank 0 would have port B here in address 6. Bank 1 has got trish B on address B. And bank 3 has got ANSL H is 189. That's what you are going to use for port B. Port B is an 8-bit bidirectional port. Bits of the trish B register, the ANSL register, determine the function of the port B, analog inputs or digital. and port B acts as a digital input output, and the fish B register determines if the pins are configured as input output. That means 0 is output, 1 is input. You can have 6 of the port P pins, 6 pins, that is P to P5, can be configured as analog input, not all of them. So these are all given on the data sheet. And in order to configure as analog input, you need to go to ANSEL H address, which is 189 hexadecimal, and you should set the value all 1. So you need to go here, this register, and set the values all 1 if you want also analog input. Okay? Port B also has some other features, and I just want to explain that to you. Each port B pin has an individual configurable pull-up register. You can use internal register or external registers. Sorry, external register, resistor. So it is controlled by this particular location, which is in bank 1, which is called WPUB, that location. And if you make this pin, this location, WPUB3, that's that, equal to 1, that means internal pull-up resistor is already connected. That means you don't, for a switch, you don't need any other resistor. You just connect the switch directly to it. That's PB3. If you make the PB3 0, this bit equals 0, then internal resistor is taken out. Then you can have this as an output and connect them without the resistor. So it's a function that you can use. You can connect them outside without using it as well if you want as an input. But this is a function available, and whenever you want it, when you are designing your circuitry, connecting to the port, this will be useful to have. Now we are going to do one example, initial example, initializing port A. How are we going to initialize port A? Here are the code. I'm not going to go through these ones, this one, you already know. I now start here. I have to select the right bank. So I'm going to select answer because I got to select that. I could tell them that I could give a command called bank cell answer. The assembler will know that it goes to the bank and select this bank because that's where the answer is there. You can do that command that way. And then you say clear W register. So I clear W register with all the zeros. Then I say that move W value to the answer. So the answer register is going to have all zeros in here. Answer register is going to have all zeros. So I made the lines are going to be, the port B, port A lines are going to be digital, port A lines are. Now I say that, okay, I go to my status register and I want to select memory bank 1. This is my memory bank 1. We know from status register, these two registers control the memory bank 1. So I could say this one is 0, this one is 1. As soon as I put that, it will select that bank. So I did that one. BCF 0, 6-bit 0, BSF means set the bit to 5. You can read through this. Set the status register to logic 1. Once I have done that, I am now selecting this particular bank. You could ask a question, well, do you want to do it this way? Can't we use bank cell trichet? Yes, it will work. I just want to show you both methods. Okay, now what I want to do is I want to make sure that all the registers are going to be output. So if here I want output, all these bits should be 0. So I clear the WL register, and if the register is already cleared, you don't need to worry. But if it's not clear, just clear again to make sure that you don't have a problem. Once you have cleared them, I move the W counter into trichet position, which is this position. All these become zeros. Now I need to go to port A. So I need to go to port A, mean I go back here, port A. Port A is where? In bank 0. I need both of them 0. So I made sure that it was 1 earlier, I set that to 0, so I go to that. So you can say now, BCF, clear the status register, 5th bit. 5th bit means this one, it become now 0, 0. These two are 0, 0. That means this bank is selected. Instead of that, you can also say bank cell port A. If you do that, it will also do that job. That's what most of you will do later, but I'm just showing you in bit position. So now I have selected this as a digital input output, and I made the port A as an output, and I'm now selected port A. Now what I do is main program starts here now. Clear F, port A. I clear port A by using that instruction. Port A will have 0. The latches would have 0. Now I move this binary pattern into W register. I have got that pattern, and then I move that value to port A. I've done it. So I've now programmed port A, and port A has got 1 0 1 1 1 0. So if you connect the LED to that line, that line, that line, and that line, the LED, all 4 LEDs will glow. And then I said, no, that's all I want to do. I don't want to do anything else. I kind of had to go to loop itself. I mean, it's not a good idea to loop itself, but just to stop there. So that's the program. That's the initializing port A. How do you initialize port A? You must go to ANSL register, select the ANSL register bank, and put the values in ANSL register. Then select the Trish A register bank and put the value in Trish A. Then select the port A register bank and put the values you want in the port A. That's all the sheet said. Now we move on to the next example. This is another example for you. In this example, you have the notes that I want to show you that reading a dip switches data and writing the LEDs, writing to the LEDs. So I have connected here in this one, in the circuit diagram, I've got port A consists of, if you look at port A, all of them consists of dip switches. If the dip switches are not closed, they will be 1, this will be 1. If it is closed, it will be 0. And all 1 belongs to turning on the light. So I have connected all the LEDs through a limiting resistor to port C. So I'm working on port A, I'm looking at port A and I'm writing the data in port C. So I have to now start to do port A and port C. I need to, excuse me, I need to prepare port A and port C. Excuse me. So port A and port C, how do you do it? So let's look at how we can actually do the programming of this particular thing. So, particular example. The program reads the data from a set of 8 dip switches on or off connected to port A, and the outputs of this data to port C, which drives 8 LEDs as shown in the diagram. If the dip switch is closed, the corresponding LED must be on. That's all it is. All basically says that read the starters here and put them back and throw them here, and that will do the job. That's all it is. So that's 2 instructions, you know. We start with start. What do we need to start? We have to select ANSL register. So we say bank cell ANSL register. And we want is a digital. So we clear ANSL register completely. So we say clear F ANSL register. So it's all digital. Now we are going to go Trish A, because we got to say it's an input or output. So bank cell Trish A. And we want port A to be all inputs. So we got to put 1s in it. There are 8 pins here in port A. So we say move literal W, all 1s into W register. Move them back, whatever the content of W register, to Trish A. So Trish A has got all ones. So that means it's ready to, port A is going to be programmed as input. Then you say, well, Trish C we need, because that's the one where output. So you can say clear F, Trish C. So you clear the Trish C as well. So you've got Trish A, Trish C. This is all ones here, all input port, this is all zeros. I've done that. Now I need to go port C, I have got to select first. So that means I've got to switch from this bank to that, and that to here now. How do I switch? I say bank select port C. So I've selected that. Now I have got to say in port C, I want to make sure everything is set to 0. No LEDs glows. So I say clear all the values on port C latches and clears, turns off all the LEDs. So all done now. Initialization all done. Everything is ready now. So we go to the main program. So main. What's the main program? You say move the content of port A, read the dip switches into W register. So you move them into W register. Okay? So your W register is going to have a value 1 0 0 1, for example, 0 0 0 1. So when you send this data out, these are the register value, and we want to make sure that the corresponding LED should glow in port C. So what I did is they are in the W register. I do, and when you read it, the problem is when you read it, when the switch is closed, these are the switches which are closed. 0, because when they close 0. But if you send that data back to the port, there's also back to the C port, all 0, therefore it won't glow. So what I do an exclusive OR operation in the W register with that value. Then what happens, this goes to 0, that 0 becomes 1 1 1 0 1 1 0. So now if I send this value to port C, LED will glow, or those LEDs will glow. So that's what I did. Exclusive OR with F, that's kind of inverting. And send the W register to port C, and light will glow. Then I go back to the program, main program again, wait and read the switches again. You are not waiting, you are just reading the switch, and then read them, exclusive OR, send them back, and so on. And that's how this program works. Here we come to the next example. This example is slightly different than before. The same principle, but slightly different. And you might ask, what is different? Now what we are doing is here, earlier we read it from one port and sent it to another port. Here now we are going to read from one of the same port, we are going to read and send also in the same port and at different bits. So you can see this program lights the LED if the switch is pressed. So here's the diagram. We only are dealing with port A. If I press this switch, LED glows. If I leave it open, LED is off. That's simple as that. That's what we have to do in this particular program. How do we achieve this is the question. I have to go back and select the AND cell register to make sure there's only a digital ports. So AND cell, bang, AND cell, clear the W register, move everything to AND cell register. That means everything is cleared. That means it's a digital. Now you go to this one. You want to select which bank. You're going to now go Trish A. You're going to have Trish A. Trish A is bank 1. So you must select 0, 1 in that position. So you go to status register, clear one bit, set the other bit. You have done that. Instead of that, you could say bank cell Trish A. You can do that as well. Then, now what you want to do is that you've got to move this particular value literally in there. That is, we are programming port A. We are going to make sure that if you program, if you look at it, these two are output, these two are input, these two are output, and I assume that's also input. So we are going to make sure that we have to put the right values in there. So what we do now is here is we select that value and then move this into Trishare. We're going to move that value in Trishare. So we move this value accordingly, 1100, 1100 Trishare. Trishare has set up the port A as input or output. Done? Now we are going to go to port A access. You can say bank cell port A, or go back and change this value to 0. And when you do that, that's what I've done. I set VCF 0, then my port, VCF 0, then my port is ready. Now I want to clear the port A, the 5th bit. I want to clear the 5th bit. Where is the 5th bit? Here. So if I clear port A 0 there, that won't glow. That's what I want to do first. I've done that. Now I'm going to keep reading this bit. If I read the bit, how do I read it? I say BTFS port A 7. So you go to port A, look at the 7 bit, and see is that bit is set or not set. If it is set, mean 1, this is not pressed. If it is 0, mean it's pressed. So that's what you are doing. So you're saying, if it's not pressed, you can't turn on the light. So you're saying, you skip the next instruction, you go here. If it is set, then it doesn't skip. It goes to the next instruction, and where you put set the bits. BSF means set value 1 at position 5 of port A. When you do that, this will start to glow. Then this is 1, that means glow. That is this part. So what you did is you jumped from here to there. Is that right? Sorry. If this is 0, then you execute this one, and that means pressed, and then you set that to 1. Sorry, I made mistake. So that's working. If it is still 1, it's not pressed, that means you skip that instruction, you jump from here to here. When you jump from there to there, what you're doing, you keep reading the status of the switch again. Has it been pressed? It wasn't pressed before. Has it been pressed again? And if you find if it is pressed, right? That means branch, if PA7 is 0, next instruction is you skip that one, you go here, and then you go back. Otherwise, you turn it off. If this is not pressed, you turn it off. So just go through this logic again yourself, and look at the instruction again, and you will have a full understanding of how you do this. So in summary, all I'm saying in this instruction is, maybe I have this particular example, I probably rushed it too quickly. All we are saying that after initialization, all you're saying, basically you are reading the port A 7. And if this button is pressed, this will be 0. If that is 0, you're saying, do the next instruction. That means you have to turn on the light. If it is not 0, then you're saying, you skip that and go here. That means it's not 0, I mean this is 1, therefore this is already 0, therefore nothing happens. And then you test it again, and clear 7, you just say, reading the status of the switch again, branch, if it's pressed, you branch here, and set 5 to clear it, and then you go back to loop. Have a look at this question again once more. If you are not sure about it, it's just condition attached, and I'm not saying this is the way to write it, but check this again, okay? Now we move on to laboratory activities. So by knowing all these examples, you can now start to do the laboratory. So first activity is get started with the MP lab, which is the which is your editor for the assembler, and the lab demonstrators will show you how to do that. Once you have done the activity 1, what's the activity 1? You must have, everybody will get a microcontroller PIC3 kit, and you need to configure port A as a digital output port. Connect 4 LEDs. You have got to connect 4 LEDs with the appropriate current limiting register. So connect them. Write an assembly program that sends this value to port A. And then you load your program into the microcontroller and observe the output. First you assemble the program, then load the program and observe the output. Show the circuit operation to the lab demonstrator. That's your first part. Very, very simple part, you know. And the second part, you configure port A as a digital input output. And I've explained that to you how to do it. Once you have finished the activity 1 and 2, then go to activity 3, which is similar to one of the examples that I have done. But this time, you are connecting the output, what you are getting is to a 7-segment display. You can then get these chips from the stores and set up this one and your microcontroller here. And for the port, you can connect all of these. Once you have done the activity 3, you go to activity 4, the clock counter. All of you have implemented this one. Now connect it to the PP node of a microcontroller and then make it as input. And every time you get when you detect this pulse, you then increment a counter inside and send it to the port, and it will display there. So that's clap counter. So this activity you can do that, after you have gone through the program that I've done, rewrite the program. My suggestion is don't just run through them and say, you understand. Rewrite them on your notebook and see whether you are able to rewrite them and understand. And then you start with these activities and see how you go. And the next chapter we will teach you how to create delay loops and how to accurately generate a square waveform, how various other conditions, and turn on a traffic light simulator. All of them we will do them in the next level. Again, these 3 things you must be familiar with them. And books are, you can look at them. These are on the web, but data sheet is the main part. That's where everything is there.